So, Jai Hind to all. Myself Dr. Uma Sharma, Assistant Professor in EC Department of Ajay Kumar Garg Engineering College. Today in this lecture of integrated circuit, I will explain about the first and second order low pass and high pass filter designing, as this topic is very important in this unit, that is unit number 2, and definitely you will get some questions, some numerical on in your university exam on the designing of low pass, high pass or even band pass filter. So, here we will learn how to design low pass and high pass filter. So, let us start. So, basically an electric filter is a frequency selective circuit that passes a specified band of frequency and block or attenuate other frequencies. So, as per our requirement, we can pass a particular band of frequency or we can attenuate a particular band of frequency. So, on the basis of input signal, we can classify filter into various categories like analog filter or digital filter. Based on the component, we can classify in active or passive filter, and similarly based on the frequency band, we can classify filter into audio and radio frequency filters. So, here the main focus is on the active filters. So, basically active filters, as the name implies, active filter are those filter where we will use active elements while designing the filters. So, here the active filter means the use of operational amplifier, transistors or FET in the designing of the circuit. Basically, by using the active components in the filter, we can achieve frequency selection as well as we can increase the gain of the filter. So, this is the advantage of active filter over passive filter. Also, here we will get the gain and frequency adjustment flexibility. Here the loading problem can be solved definitely because of high input impedance of op-amp we will use in the active filter. So, there is no loading issue, and definitely the active filters are cheaper than the passive filters. So, just come to the point here. Let us see the circuit diagram of first order active filter, and here the category is on the basis of particular specified band. So, let us say the filter is able to pass the particular low frequencies. So, the filter can be named as low pass filter. From this diagram you can see that this is the frequency response. On x axis there is frequency and on y axis this is the gain. So, when we draw the graph between frequency and gain, from this graph you can see that at very low frequency, starting from the 0, the gain of filter is constant, and after a particular frequency, let us say this FC, the gain start reducing. So, there is a slope from this FC to the FC onwards, and this slope is minus 20 dB per decade. So, that means after a certain frequency the gain start reducing. So, this point is known as center frequency or corner frequency or cutoff frequency, and the band where gain is constant is known as pass band, and in other word we can say this band is stop band. This is stop band because here filter, in this stop band the filter will attenuate all the frequencies. So, definitely gain is very low in stop band, and in pass band gain should be constant. So, here you can see that. So, to get this response we are having two options, like we can implement the circuit using only passive components or we can use active components. So, in designing of active filter we are using this op-amp along with the resistor and capacitor, where if we want to design a filter using passive components only, so the op-amp will not be there and we can design the filter using R, L and C. But in passive filter, like first order low pass passive filter, the gain is very low, although the frequency selection is same. So, here in this active filter design there are two parts basically. One is frequency selection network. So, this R3 and C1 is forming a frequency selection network, whereas this op-amp along with R1 and R2 is forming a amplifier. So, here this can be known as this is frequency selection and this is amplifier. So this is a combination of frequency selective network plus amplifier. Okay, so here you can see that the input signal, like this is the input signal, it is applied at non-inverting node. So just note down this point, the input signal is applied at non-inverting node, and at inverting node 2 resistors are connected, and definitely configuration can be named as non-inverting amplifier configuration because input is applied at non-inverting node. So active filter design is basically based on the non-inverting amplifier design. Here this RNC, this is the RC network, and which is used to select the particular band of frequency. So R is connected with the input signal, and this C is connected in series with this R3, and this RC network is forming a low pass filter. So this is low pass filter stage and this is amplifier stage. So this is how you can design the circuit for first order low pass filter. So for first order low pass filter, C is the center frequency, this is the center frequency, and AF is the gain. This one you can see that this is non-inverting amplifier configuration. So the gain can be, AF can be the gain of non-inverting amplifier, that is RF by Ri, and here RF is R2 and on V in, that is the gain. We can define the very less for this when F is very less. So for this particular point, if you put the F very less than to FC, then you can see that there is this term will become very less and this under root will become almost unity, and you can see that V output upon V input is nearly equals to AF. So for first case, this is case 1, the V output upon V in, that is the gain, and that is equals to AF. So from this diagram you can see that at low frequency gain is equals to AF. Now let's say the second case, when F equals to FC, put the F equals to FC over here. So this will become 1 and 1 square is 1. So you can write AF upon under root 1 plus 1. So the V output upon V input will become AF upon root 2, and that can be given as 0.7 of AF. So from this graph you can see that this is the point when F equals to FC, the gain is roll of 0.707 of AF. So this is the basically 0.07 of AF for this gain. Similarly, you can see the high frequency band. So at frequencies when F is very greater than 2 FC, you can see that if F is very high, that means this term will become high as compared to 1, and definitely that will reduce the overall gain. So in that case, whenever your F is high as compared to FC, your center frequency, your V output upon V in, that is the AF, that is the gain, will always be less than AF. So this is how you can justify this graph from this diagram. So this is the theoretical concept. Now let's see how to design a low pass filter. So these are the designing rules for designing any filter. So let's say the first point is select or choose a value of high cutoff frequency. High cutoff frequency means the frequency which is considered as high, means up to that frequency the filter will pass all the frequencies, and after that frequency, after that high cutoff point, the filter will attenuate all the frequencies. So select the frequency for which you are going to design a filter. Now let's select the value of capacitor C, and that should be less than 1 microfarad, because on integrated circuit, on IC, it is a good practice to use less value of capacitors, because at high value the size of the capacitor is very large. So we generally avoid to use large value of capacitors on the integrated circuits. So definitely you have to select any value of capacitor, but it should be less than 1 microfarad. And these are the mylar and the tantalum other material for design for making the capacitors. So they are recommended. Now let's calculate the value of R, because in the designing part, basically we are going to calculate the value of R3, C1, R1 and R2. So again I am repeating, if you want to design a filter, so first we should know the circuit diagram of the filter. Let's say we have to design a first order low pass filter. So everyone should know the circuit diagram, that non-inverting configuration of op-amp, and here the objective is to find out the value of these components like R3, C1, R1 and R2. So to find out these values, we have considered the value of C1, that is less than 1 microfarad. Now we have to calculate this R. So to calculate this R, just use the formula Fc equals to 1 upon 2 pi Rc, and here we know the value of C. So R will become 1 upon 2 pi Fc into C. So Fc we have assumed in step 1 and C we have assumed in step 2. So easily we can calculate the value of R. So this is how we have designed the frequency selective network. Now we have to design the amplifier part. So for designing of amplifier network, we have to find the value of R1 and R2. So we can decide the gain of the filter, and we know the formula for gain because it is non-inverting configuration. So the gain formula is 1 plus R2 by R1. So now let's assume the value of any of the resistor, like let's say R1, and we can calculate the value of R2 if we know the gain of the filter. So in the last step we have to assume the gain of the filter, and on the basis of this non-inverting amplifier formula, just assume the value of R1 and calculate the value of R2. So this is how we can design the amplifier network too, and just put these value on the circuit diagram and your designing will be completed. Now come to the second order designing, second order filter designing. So for the second order filter, the only change is here, I think it not visible in your screen, but here at the input of R1, input signal is applied, and here the frequency selective network consisting of R1, R2, C1 and C2. Because it's second order, so that means there are two RC components are there. One RC is providing one pole, so known as first order filter. Two RC are providing two poles and are known as second order filters. The amplifier section is same. You can see that the amplifier section is same. Here also two resistors are connected, RA and RB, and they are providing gain of 1 plus RA by RB. So definitely the amplifier section designing is same, but now for the designing of second order filter, we have to calculate the value of R1, R2, C1 and C2. So these are the formulas. So directly I have written over there. Fc is 1 upon 2 pi under root of R1, R2, C1, C2, and if all the resistor and capacitors are same, then Fc again is equivalent to the first order filter, that is 1 upon 2 pi Rc. Just see the frequency response of second order filter. So here you can see that this red line represents the first order frequency response. Once you add our second pole, that means we are increasing the order of filter, so the response will move like this, in this direction, because the slope is having, now the slope has been changed and this is minus 40 dB per decade. And similarly, if you want to design third order filter, then that will become minus 60 dB per decade. So this will move in this direction. And for the ideal filter, basically for ideal filter, the response should be like this, frequency and gain. So as we increase the order of filter, the frequency response will move towards the ideality. So this is how we can get the frequency response of second order filter. Now let's see the designing step for the second order filter. So steps are same, but here we have to calculate R1, R2, C1, C2, and again we have assumed the equal component filter design. So R1 equals to R2. So basically all the three steps are same. First you have to select the frequency, then you have to calculate the value of R1, R2 on the basis of selection of C1, C2, that we have to select less than 1 microfarad. So we can calculate R1 and R2 easily by using this formula. But in the fourth step, generally in second order filter, we are having different responses like Butterworth filter response, Chebyshev filter response, Wessel filter response. So if you have given a gain, particular gain, let's say design a filter for the gain of 4, then definitely you can design it for the gain of 4. But if gain is not given in the question, in that case, for second order filter design, second order Butterworth filter design, the gain is 1.586. So for the second order Butterworth filter response, the gain is 1.586. So you have to remember this value for the Butterworth filter. So for this Butterworth filter, the gain is 1.586. So we can calculate the value of this, value of RA and RB based on gain of Butterworth. So like AF is equals to 1 plus RA by RB, and that is equals to 1.586. So this is how we can calculate the value of RA and RB by using this gain formula for Butterworth filter. So in second order designing, there are two steps. If gain is given, then definitely you can equate 1 plus RA by RB by the given gain, or if gain is not given and or it is said that you have to design a Butterworth filter, then definitely you have to consider 1.586 as the gain of the second order Butterworth filter. Now this is the designing of low pass filter. Similarly, you can design a high pass filter too. In high pass filter, there is only one change in the designing, that the places of R and C are interchanged. Like in first order filter, this is the place for R and this is the place for C. So here I have changed the position of R and C. So for the first order filter design, everything is same. Now the input signal is passed through a capacitor first, then goes to the non-inverting node of operational amplifier. The inverting node is same. The connection at the inverting node is same. It is again connected with R1 and R2. So this is how you will get high pass response. High pass response means the filter which is able to pass high frequency band and attenuate the low frequencies. So from this graph you can see that at low frequency gain is reducing, but at high frequency gain is constant. So just by replacing R and C in low pass filter design, we can design a high pass filter. So for high pass filter 2, we can see the gain which is equal 1 plus R2 by R1, similar to the low pass filter, and the voltage gain V out upon V in can be derived, and it is equals to AF F upon FC upon under root 1 plus F upon FC whole square. So here in numerator there is a term F upon FC. So now let's see what happen when F is less than FC. So if F is less than FC, in that case you can see that if this F is less, that means this AF will multiply with less than 1. So definitely this V out upon V in will always be less than AF. Similarly, when we equate both F equals to FC, so here you can see that will become 1 and this is also 1. So the V out upon V in will become AF upon root 2, and this is similar to the low pass filter 0.707 of AF, and this is known as cutoff frequency of the filter. So here the gain reduced by 3 dB. Basically this, if we convert it into the dB, then it will become 3 dB. And at very high frequency, you can put the high frequency in this formula, and you can see the V out upon V in is almost equals to the AF. So from this explanation, from these explanations, we can see that this graph can be achieved. So this is the graph for high pass filter. This is the second order filter design. So nothing different in this too. So again here the two RC components are used to get the second order filter response. The inverting node is same, connected with RA and RB as in low pass filter or in first order filter. The only change in this non-inverting node terminal, at this non-inverting node now two RC networks are connected. So this is the frequency selection network consisting of R1, C1, R2, C2. And from this circuit again the gain can be written as 1 plus RA upon RB, and the cutoff frequency can be written as 1 upon 2 pi under root R1, R2, C1, C2. And if resistor and capacitor values are same, then FC can be written as 1 upon 2 pi RC. So from this circuit diagram we can see that the frequency response, like for first order the gain roll off rate is 20 dB per decade, and second order the gain roll off rate is minus 40 dB per decade, and similarly for the third order filter the gain roll off rate will become minus 60 dB per decade. So this is how here the response move in this direction, and again this will equals to high pass response. So high pass response means the filter will attenuate all the low frequencies and pass all the high frequencies. So this is the ideal response for the high pass filter. Now let's take some example. Design a filter, low pass filter or high pass filter. I have taken one example for a cutoff frequency of 2 kilohertz, let's say. This is the question. So if it is not given in the question that first order or second order, so you can design either first order or second order, but in your syllabus it is mentioned that you have to study second order filter. So if it is even not given in the filter, but you have to design second order filter. So first of all we will identify the order of filter. So let's say it's second order filter. So if it is given in the question, design a second order, then it's okay. If it is not given, then you have to design second order. If it is given like you have to design a first order, then only you have to design first order. Otherwise, in any case, you have to design second order filter. So for the second order, suppose question can be same, like for low pass filter for the cutoff frequency of 2 kilohertz and for high pass filter for the cutoff frequency of 2 kilohertz. So you can understand with this graph, let's say it is talking about low pass filter. So that means this is 2 kilohertz frequency and gain. So that means you have to design a filter which is having this type of response. Cutoff frequency is 2 kilohertz and the filter will pass all the frequency up to 2 kilohertz and attenuate other frequency. This is for low pass filter. And similarly, if you have to design a high pass filter with the center frequency or cutoff frequency of 2 kilohertz, that means the filter will attenuate all the frequency below 2 kilohertz and will pass all the frequency after 2 kilohertz. So that will be the frequency response. So question can be same, but you have to understand what is the meaning of low pass and high pass filter. So let's say design a low pass filter, second order low pass filter. So the first step after identifying the order of filter, just select the frequency. So FC is equals to 2 kilohertz. Just write it because it is given in the question, that is 2 kilohertz frequency. And now in second step you have to write the formula for cutoff frequency, that is 1 upon 2 pi RC, and here I have assumed that R1 equals to R2 and C1 equals to C2. Now assume, next step, assume C equals to less than 1 microfarad. So let's say that is 0.1 microfarad. So this is the value of C. Now we are having the value of FC, that is 2 kilohertz. So 2 into 10 to the power 3, that is equals to 1 upon 2 pi R into 0.1 into 10 to the power minus 6. So from here we can calculate the value of R, because only the R is unknown. So from here you can calculate the value of R. So this is how we have designed the frequency selective network, the value of R1, R2, C1, C2. Similarly, for the designing of gain, so here the gain is missing, but you have to design second order filter. So for second order filter, we know the Butterworth filter response is better than other responses. So we will design Butterworth filter. So for the designing of amplifier part, just assume AF is equals to 1.586 and this AF is equals to 1 plus RA upon RB, that is equals to 1.586. So RA upon RB is equals to 0.586, and this is how RA equals to 0.586 into RB. Just assume the value of RB less than 100 kilohertz, 100 kilo ohm, any value 100 kilo ohm, and easily you can calculate the value of RA. So you have to assume this value, this is important, you have to assume this value, and this RB is totally different from this R. This R we have calculated for the frequency selective network, and here this RB is the amplifier network. So this is how you can calculate the value of RA and RB, and just put these value RA, RB on this network, R1, R2, C1, C2, RA and RB. So this is how you can design any equation related to first order, second order, low pass and high pass filter. So this is all the basic concept about the filter designing of first order, second order, low pass and high pass filter. Similarly, you can design band pass and band reject. In the further lectures, I will explain how to design band pass and band reject filter. Thank you so much.